Hello, welcome to Math 6, Lesson 1.4, Prime Factorization. This is Miss Jones of Bell Middle School. We have objectives today. I will be able to sort prime numbers versus composite numbers. I'm going to have to figure out what those are first, though, right? I will factor composite numbers into prime factors using factor trees. I will find the patterns of divisibility rules by skip counting. So my first thing is I'm going to define a couple of things. I'm going to define what a factor is and what a factor tree is. So a factor is when whole numbers other than 0 are multiplied together. Each number is a factor of the product. So whole numbers, or just numbers, multiplied together to get the product. So simply 2 times 4 equals 8. These are the factors, right? Those are the factors. This is the product. A factor tree is simply a nice, convenient way to show factors and getting down to in branches, so to speak. So if I made a factor tree of 24, that would be 4 times 6. 40 might be 4 times 10. Those are factor trees. They're not prime factorization, but those are factor trees. I can make them longer because 4 actually equals 2 times 2. I can add extra branches to my factor tree. 6 is 2 times 3. So 2 and 3 are both factors of 6, and 2 and 2 are both factors of 4. Therefore, 2 times 2 times 2 times 3 equals 24. So all of these, 2 times 2 times 2 and 3, are all factors of 24. If it were to make my branches longer on my 40, I could go 2 and 2 because 2 times 2 is 4. I could go 2 and 5 because 2 times 5 is 10. 2, 2, 2, 5 are all factors of 40. 2 times 2 times 2 times 5 equals 40. Remember our last lesson said that you could also write that as an exponent. 2 to the third times 5 equals 40. That's just a little review from last lesson. Prime numbers. So now that we've talked about what factors are, we can talk about what prime numbers are. Prime numbers are any number that doesn't have factors. It's any number that doesn't have factors. So any number that doesn't have factors. Oh, and by the way, it has to be greater than 1. Greater than 1. So it has to be greater than 1. So for instance, my prime numbers would be the following. My prime numbers would be 2, because that has no factors, 3, 5, 7, 11, 13, 17, 19, 23. Those are all prime numbers. I said they don't have factors. They kind of have factors because you can always say that 23 is 23 times 1. And you can say 19 is 19 times 1. But they don't have any factors other than 1 and the number that they are. So they don't have any other factors. There's nothing else I can multiply other than 1 and the number. Composite numbers, on the other hand, definitely do have other things that you can multiply. They definitely do have factors. So composite numbers are numbers that have more than just 1 and the number, as factors. right? So it has lots of numbers that could be. So for instance, composite numbers would be 4, 6, 8, 9, 10. Anything that I can multiply two numbers to get to that number. I can multiply a 4 and a 2 to get to 8, therefore it's a composite number. Okay? Skip counting is one way that we're going to figure out what numbers are prime, what numbers are composite. After I skip count for a little bit, it'll help me remember what I can divide numbers by what numbers, and so then I'll know that they are composite numbers and not prime numbers. So let's practice skip counting. I know in elementary school you did a lot of skip counting. So skip count twos. 2, 4, 6, 8, 10, 12, 14, 16, 18. What do you notice when you skip count all those numbers? What's the pattern here? They're all even. They're all even numbers. So they're all even numbers. So anytime I see a number that's even, I'll know that it's a composite. So it'll be a composite if it's even because 2 is a factor. Okay? So let's look back at our prime numbers. 3 is not an even number. 5 is not even. 7 is not even. 11 is not even. 13 is not even. So that's how we know those are prime numbers, or one of the reasons we know. Let's look at 3s. How we know if 3 is a factor of a number. So let's do some skip counting and see if we notice some patterns. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39. Patterns. This is a tough one. So the pattern here, I'm going to give you a hint. What if you added digits together? Do you notice anything when you add the digits? Okay, I'm going to add the digits. So when I add 3, it's just 3. There's only one digit. There's only one digit here, so 6, 9. But here I get 1 plus 2, so that's 3. Here I get 1 plus 5 is 6. 1 plus 8 is 9. 2 plus 1 is 3. 2 plus 4 is 6. 2 plus 7 is 9. 3 plus 0 is 3. 3 plus 3 is 6. 3 plus 6 is 9. And 9 plus 3 is 12. So let's look at these. Up until this point of 12, these numbers 3, 6, 9, 3, 6, 9, 3, 6, 9, 3, 6, 9, all of these numbers are very easily to see that they're divisible by 9 or by 3. They're all easy to see. 9 we know is divisible by 3. 6 we know is divisible by 3. The pattern that we want to look for to see if it's divisible by 3 would be to add the digits and see if that number is divisible by 3. And it'll be pretty easy to see. 9, 3. If you get to a bigger number like 12 and you're not positive if it is, do it again. 1 plus 2 is 3. So it just keeps going over and over. The next number, so say I get to 333. I add those 3 digits together. I get 3 plus 3 is 6, plus 3 is 9. So it is divisible by 3. Okay, so we know that 3s have this. 4s? Let's talk about 4s. Do we really need a divisibility rule for 4? I want to say we really don't, because we know that 4 using a factor tree is 2 times 2. So anytime that there might be a way that you can tell if it's divisible by 4, but really if it's divisible by 2, we don't need the 4s. 5s, we don't need a special rule for 5s, right? We don't need that special rule. Fives. Fives are different because they are not divisible by 3 and they are not even. But let's do some skip counting. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. To know if this is divisible by 5, what pattern do you see? I see that it's either going to end in a 5 or 0. Okay, so if the number ends in a 5 or 0, it is divisible by 5. And you probably already knew that. I imagine that's one that you caught on to. Do we need a special divisibility rule for 6? Remember, 6 in a factor tree is 2 times 3. We already did the divisibility rules for 3 and 2, so I don't think we need to do for 6. 8, make a factor tree for 8. 4, 2, 2, 2. It's all 2, so if it's an even number, you're going to use a 2. You're not going to worry about an 8, so we don't need an 8. 9, the factor tree for 9 is 3 times 3. We already did 3, so we don't need a divisibility rule for 9. But 10, 20, there is no 1 for 10, although you could even argue that 10 is 2 times 5, therefore you can always use your 2's. But this is a pretty easy one, 30, 40, 50. We see that if it ends in a 0, it is divisible by 10. Okay? Prime factorization is one of the last things I'm going to talk about. Prime factorization is a special way to use these factor trees. So the special way that you're going to use these factor trees is you're going to take any number and you're going to get it down where you cannot get it any smaller. So we're going to branch down as much as possible. So let's take a couple of examples. Let's take, what do we want to take? Let's take 70. It's an even number and it also ends in a 0. So I could do 10 because I know it ends in a 0. So 10, and then I would have to figure out how many times 10 goes into 70. In this case, it's 7. I'm not done though because 10 is not a prime number. So I can divide 10 into 2 and 5. Can I divide 7 into anything? I cannot. So my prime numbers are 2, 5, and 7. So 2 times 5 times 7 equals 70 is the prime factorization for the number 70. 2 times 5 times 7 is the prime factorization for the number 70. Let's try 45. 45. Using our divisibility rules, I know that it ends in a 5, so it must be divisible by 5. Okay? If you don't know how many times 5 goes into 45, it's totally cool. You can do this lots of ways, right? We can go back to our skip counting. We can look at our skip counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. At the 9th time, I got to 45. So I know it's 4 times 9. Skip counting is a fine way to do multiplication if you don't know your multiplication. That's something that I would love to get us to have memorized. Is this a prime number? Is 5 a prime number? Yes, there's nothing I can multiply 5 by to get smaller numbers. How about 9? I can multiply 3 and a 3. So my prime factorization of 45 is going to be 5 times 3 times 3 equals 45. There's my prime factorization of 45. The last one I'm going to do is 88. 88 is an even number, so I can use my 2's. I know it's going to be divided by 2. This is a prime example. If I'm not sure how many times 2 goes into 88, there's lots of ways I can figure it out. If nothing else, I can always do a long division like this. I can skip count up to 88. You can make a number line and you could count like this. until you got up to 88, and then count how many 2's you went. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and keep going till you got to 88, and then count the number of jumps that you had to make on a number line. Eventually, you're going to get to 44. 2 is, in fact, a prime number, right? We know 2 is a prime number because there's nothing smaller, but we don't think 44 is. It's still even, so I can go 2 and 44 divided by 2. Well, half of 40 is 20, and half of 4 is 2, so 22. Again, 2 is prime. 22 is not prime, so it's even, so I can go 2. 2 goes into 20 10 times, and 2 goes into 20, or 2 goes into 2 one time, so 2 times 11. So now I'm thinking prime numbers. I know my 2 is prime. Is my 11 prime? Is there anything I can multiply 2 numbers by in order to get to 11? Nope, so that's prime 2. So the prime factorization of number 88 is 2 times 2 times 2 times 11 equals 88. That is the prime factorization of 88. You can also write this as a review from last unit or last section is 2 to the third times 11 equals 88. Okay? Last thing I'm going to do is quickly look at some vocab just to remind you. A composite number is a whole number greater than 1 that has factors other than 1 in itself. So they're all numbers that you can, in fact, do a factor tree for. So, for instance, let's start back here. 20, I can do a factor tree. That is 2 times 10. And 10 is 2 times 5. There's my factor tree. 18, 2 times 9. There's my factor tree. So each one of these I could do a factor tree for. So if you think composite number, if you think of the word composite means it's a combination of things. It's a combination of different numbers. So think combination of numbers, and you can make a tree out of it. Okay, so if you can remember those two things, that composite, combination of numbers, that you can make a tree. Okay? Prime means number one, uno. You are the prime cut of meat. You're the best meat. You have the prime membership. If you have the best membership, if there's only one of you, you are the prime minister when you are the head of England, I believe. And so you are the prime number one, meaning there's only one. There's only one in itself. So there's only one. When you think prime cut, the highest thing. The lowest thing in this case, you can't get any smaller. You can't cut these down into a factor tree. So prime meaning one, okay? There's only one and the number. So you cannot do a factor tree. So no trees. There's no trees for prime. Okay? Factor. The factor, you've probably used this word your whole life. It's just the things that you're multiplying, right? The things you multiply. The things you multiply. And that is the product. So a factor in terms of a factor tree just means that it has branches, and these are factors. All of them are factors, and the tree is just the way that we show it. A factor pair, I don't think I mentioned yet, it's just when there's two of them, right? So 2 and 5 are factors of 10. If I said 12, you tell me that the two factors are 3 and 4, or you tell me that the two factors are 2 and 6, but either way, they're a factor pair for the number 12. Factor tree, as we talked about, it's just a diagram going downward that shows prime factorization. So you're going to get down as far as you can. Typically, we always circle when we get down to the prime. Okay, so you're going to circle when you get down to the prime numbers. Prime factorization is just what you get when you get to the bottom of the tree. So this here is the prime factorization. Oh, it's the same number, 60 and 60. Let's do one more example. Let's do, I don't know, what do you want to do? 232. So 232, is an even number, so I know there's going to be 2, and there's going to be something else over here. Half of 232. I know half of 200 is 100, so there's going to be a 100. So half of 200 is 100, and half of 32 is 16. I know that, but if I didn't know that, then I might say half of 30 is 15, and half of 2 is 1. So when I add these together, I get 116, right? So 116. Okay? Oops, add those together there, not there. I get those are the half of all of the chunks. So that's just another way to think of this. You don't have to do long division. I'm getting closer to my prime, but I'm still not there. 116 is still an even number, so I can do 2 and 116. So what is half of 116? Well, I know half of 100 is 50, and I know half of 16 is 8. So the two of those together must be 58. Okay, I'm going to add those together. I get 58. That's another way that you can do division without having to do long division. Half of 58, or 58 is an even number, so again, I'm going to go do 2. How many times can you take half of 58? 58, I know half of 50 is 25, right? Because 2 quarters is 50 cents, and half of 8 is 4, so when I put those together, I get 29. Well, that's a weird thing. 29. So half of 50, or 29. Now, is there anything I can do with 29? It's no longer a even number. Is it divisible by 3? So is 29 divisible by 3? If I add my 2 digits together, 2 plus 9, I get 11. So it's not divisible by 3. Is it divisible by 5? Does it end in a 5 or a 0? It's not divisible by 5. It's not divisible by 2 because it's not even. So it must be prime. So even it must be a prime number. So I'm going to circle my prime numbers. 2, 2, 2, 2, and 29. So prime factorization of 232 is 2 times 2 times 2 times 29, which equals 232. That's the end of our lesson today on prime factorization. We got this.